We're going to dive into the oxygen nucleophile addition to CO stuff right now. And I've cut this down a lot, so it should be pretty short. And I have built in a separate mini lecture that just goes through examples. So let's get started. Oxygen nucleophiles is the area of biochemistry that's all about acetals and ketals, hemiacetals and hemiketals. We'll look at nitrogen nucleophiles separately, but as you've seen in class, the mechanism is all the same and it's all totally rationalizable based on what we've already learned. Now, before we get any further, I just want to throw up this slide so you can see what the answers to the last mini lecture's random reactions are. So I will let you look at that, pause this, see that, and moving right along, let's dive in. This is biochemistry galore. Basically, what we've seen already is that if I have a carbonyl electrophile, nucleophiles like to add to that. Now I can't just say H minus, it really needs to be something like lithium aluminum hydride or sodium borohydride. But that basically will reduce my carbonyl to the alcohol. Or if I have a Grignard or organolithium, so again I really should specify my counterion here. That hard nucleophile is going to add to my CO electrophile to stick irreversibly and give me a new carbon-carbon bond and an alcohol. Now what we look at is the soft nucleophile alcohols in particular. Alcohols add under acidic conditions to the carbonyl electrophile in a reversible fashion to give you first the hemiacetal and then the acetal. Now I should point out that Cardy doesn't make any mention of ketals or hemiketals. Nomenclature is important in biochemistry, really important. So let me first point out that you can keep these hemiacetals and hemiketals straight by recognizing that there's the hydroxyl group on there. So just remember the H, the hydroxyl OH means hemi. What's the difference between an acetal and a ketal? Well, the difference is this right here. If it was a ketone, then it's a hemiketal and a ketal. If, on the other hand, this was a hydrogen, then it's a hemiacetal or acetal. Aldehyde acetal. Just remember the A. So ketals and hemiketals from ketones. Acetals and hemiacetals are from aldehydes. And of course the aldehyde means that that is an H attached there. Okie doke. So formation of acetals must take place under acidic conditions. You have to have the proton there. And remember that TSOH is an acid, not a base. You have to have a proton there to make a good leaving group. So I'm just going to spin out here onto the chalkboard to make this a little bit easier to follow. So here we have a prototypical carbonyl. This is going to, we'll make it an acetal. So here's an aldehyde, and I am adding this alcohol. And what's interesting about this alcohol is that it's all tied up into one molecule. I've got two equivalents of the OH in one molecule. But we have an electrophile, and our other electrophile is our catalytic amount of acid, so acid base always wins. And what do we see? We see protonation of our carbonyl by that acid. Now, why doesn't it protonate the alcohol, the diol? I can assure you it does. Everything in here is happening in equilibrium. So, yep, it makes good sense, absolutely fine sense, that the lone pair on my oxygen gets protonated, but it gets deprotonated too. Alright, once the carbonyl is protonated, what nucleophile do I have present? Well, I have a large excess of my alcohol, and so that is going to allow me to attack. And note the seamless transition to non-line structure here. Alright, so here is my intermediate. As soon as I see that, what I should zoom in on is the fact that I have a protonated oxygen. Boy, would that like to be deprotonated. What is present that can deprotonate it? Well, one thing that is present that can deprotonate it is that diol. The alcohol is happy to be a base, and just go ahead and remove that proton. That will give me my neutral intermediate here, and what you can see at this point is that I have, and I'll make it obvious here, woohoo, there is my hemi acetal. Again, hemi because I've got the OH group attached, and it's an acetal because there's that hydrogen on that carbon. Well, now what can happen? Well, I'm under acidic conditions, so I'm going to protonate something. And I can protonate here, I can protonate here, I can protonate here. You know what? It all makes sense. They're all reasonable places to protonate. And in fact, they'll all be protonated. What I want to see happen here is, since I have a huge excess of this guy, I'm eventually going to be losing this guy. In other words, my excess of the alcohol is going to push out the hydroxyl group. So protonation is going to take place. It's not that way. To convert this to a good leaving group. And now I'm going to switch back to line structure because I'm running out of room. And there's my intermediate. And what do you think would happen next? Well, the exact same thing that would happen in Chapter 9. I have a fantastic leaving group. I'm under protic, very polar conditions. So, not that. Never can keep this straight. I lose that leaving group. I'll just redraw my intermediate here. I'm going to lose that leaving group like so. Absolutely reversible. And sure enough, I get a carbocation. And at this point, it should be painfully obvious that I have a fantastic electrophile and a nearby nucleophile that would oh so happily react to give me a 1, 2, 3, 4, 5-membered ring. So I got CH3, CH2, CH2, C, O, CH2, CH2, O. There's a hydrogen sitting on the edge there, and here's my aldehyde hydrogen. So this intermediate, again, every time you see that proton hanging off an oxygen that's protonated, where it has a positive charge, whew, please deprotonate it. Now I'm just going to use a generic B for base, but my base is, of course, my alcohol. So, deprotonate it, and what do I have? I have an acetal. So here is my alcohol. It came from that diol. And here is my aldehyde. Note that that carbon is at the oxidation state of a carbonyl carbon. It's still essentially a CO double bond. It just happens that the two single bonds are now single bonds instead of the CO double bond. Let's figure out the oxidation state. COH R, so that would have been -1, -1, +1. What's this one? +1, -1, -1, +1. Haven't changed anything. Not an oxidation, not a reduction. We're at the same oxidation state. Okay? So the mechanisms associated with this whole chapter are all the same as we've seen in class. So the key points that you want to take home with you are: you have to have the proton present to kick out or lose whatever leaving groups you're making. And most importantly, since the whole thing is all reversible, you have to have a huge excess of your solvent to push the product all the way to the right. Remember that we're talking about an enormous number of steps here, and they're all pretty similar. But ultimately, you're going to end up at a stable final product. And all the rest of these are equilibrium. So, if you want to make the acetal or ketal, you are basically starting with an aldehyde or a ketone, and adding a huge excess of an alcohol to make your acetal. To get rid of the acetal, so here's my acetal. I want to go back to my aldehyde or ketone. I do that by kicking out the alcohol by use of a large excess of water. So I'm looking at this, I'm saying, oh, I'm hydrolyzing an acetal here. What? How can you tell there's an acetal? It's kind of confusing, this one. What you're looking for is that carbon that's at the same oxidation state as a CO double bond. You're looking for a carbon with two oxygens attached to it. And right there is my carbonyl carbon. And where is my alcohol? My alcohol is right here, that diol. So, by addition of a large amount of water and a catalytic amount of acid, I can hydrolyze that ketal to give me the ketone and the alcohol. And you should work through the mechanism to convince yourself of that fact. So, next, more of the same, only though it's nitrogen. But wait! To wrap this up, we need a joke. We're talking about aldehydes and ketones all over the place, so needless to say, we should review our aldehyde nomenclature. This is formaldehyde. This is casual aldehyde. Yeah, absolutely. All right, we will see you in class.